Okay, so in the previous video, we talked about Newton's three laws, and now in this video, I'm gonna explore the consequence of the second law. Okay, so if I have if I give you the force as a function of time, right? And Newton's second law says that the force as a function of time changes the momentum such that F equals dp over dt. Then the most obvious thing you can do is to integrate both sides with respect to time. And basically, you end up getting that the left-hand side, the integral of force with respect to time, is the change in momentum, right? And this is the left-hand side is what we define as impulse, right? So in other words, impulse is any impulse that you apply on an object changes the momentum, and impulse equals change in momentum. So this holds as a vector equation, meaning that for each component of the force and momentum, right, it holds true. So if I integrate the force, if I do a definite integral of the x component of the force over some time ta to tb, then that equals to the change in momentum in the x direction of the particle. Okay, there's a bit of okay, and before I go on to that, this applies for all three coordinates. So often we write it something like that. We write this vector on top of f to tell me that it's a vector quantity, and we write this arrow on top of p to tell me that it's a vector quantity. But if you're confused by this, just expand it component-wise for each component of the vector x, y, z. Something to note is that when we do this derivation, right, we see that the first step over here is just integrating both sides with respect to time from ta to tb, right? Ta to tb. And the reason why we integrate the reason why the two endpoints for the definite integral are time coordinates is because we are integrating with respect to time, right? If we integrate with respect to, let's say, dx, then the two endpoints must be position coordinates. And the reason why this is so, the simple reason why this is so is because when we integrate, let's say, a function small g of x, right? G of x dx, we get big G of x, right? And we plug in the two endpoints. We plug in the two endpoints. This function, big G of x, right? It takes in a position. So these coordinates better be positions. If not, it wouldn't make sense to substitute a time into a position or position into time, right? So the upshot of this is that when we integrate something, we always need to look, number one, what is the variable we're integrating with respect to, right? Is the function, is the integrand, the thing inside that we're integrating, is that a function of the variable that we're integrating with respect to? They must match. If not, we cannot perform this integral, right? So the integrand's parameter must match the variable of integration. And number two, does your endpoints for your function, does it match the variable that you're integrating with respect to? It must match, because if not, when you're finding area under a graph, right, you end up substituting things that don't make sense, right? You end up substituting a time coordinate into a position variable, and your units just don't make sense. Okay, so that's just the first thing to note. And the reason why I'm emphasizing this, even though it seems like a rather trivial fact, is that when we do change in variables, right, when we do U substitution, right, this technique called U substitution in integration, right, when we do it, we must change the endpoints accordingly as well. So if we take a look at the simplest example of U substitution over here, U substitution is fundamentally the undoing of the chain rule in differentiation. So this is differentiation. A chain rule in differentiation corresponds to the U substitution in integration. When we do U substitution, right, we see that we are kind of so-called cancelling the dt over here, but because of that, right, we're left with this vpx, And when we're integrating, now we're no longer integrating with respect to time. Right? Previously, we're integrating with respect to time, so the two endpoints over here are time coordinates. But after we change variables such that we're actually integrating with respect to momentum px, right? The endpoints of your momentum must change accordingly as well. And there's a bit of nuance here when we talk about whether this px is a monotonic function of time. If it's not a monotonic function, actually we need to decompose it into two paths and whatnot. But for most purposes, it's enough to think of it as just substituting. So that because now we're integrating with respect to px, we need to change the bounds of integration from ta to tb to px of ta, px of tb, right? The momentum at the two endpoints, at the two time values, the momentum. And after doing that, right, we can just perform the integration. We get this, and let's just change the momentum. So from this example, right, not only do we define what impulse is, but I use this example to highlight, right, the importance of changing your two endpoints of integration when doing a definite integral. Okay, so that's impulse, and you calculate impulse when you're given f as a function of time.